Yeah, hello everyone. This is Dr. Abdul Pasha, Assistant Professor, Institute of Aeronautical Engineering, Hyderabad, from the Department of Electrical and Electronics Engineering. So we discussed some points regarding AGC earlier. So that will cover about one area power system network. Here it is about automatic generation control in two area power system network. So this describes some brief description about that, and it will explains how AGC will influence in two area power system network. What are the parameters we are going to consider, that we will discuss in this class. So coming to AGC in two area power system network, automatic generation control is a system that will be used in multi-area power systems. This is to maintain the system frequency and tie line powers at their nominal cases or nominal values. So AGC is very much important because it helps to prevent the system frequency that should be deviating from its nominal value, and which can happen when the generated active power becomes less than the power required or power demand. So here are some of the considerations of AGC in a multi-area system. So those are tuning techniques, that is multi-technique tuning method is used to increase the stability of the AGC system. So this includes basically tuning the gains of the PID controllers and its sine cosine algorithms like SCA, particle spam optimization methods PSOs, and Gray-Wolf optimization methods, and finally genetic algorithm methods. So this will make the AGC as suitable tuning methods. Control strategies. What are the control strategies we are going to introduce in two-area power system network? So some of the control strategies for AGC in a two-area power system includes using a proportional integral derivative controller, which will be treated with filter that should be considered for each area. So using the PID ANFIS method and DG, this will be ready to limit the number of changes. And also it will be considered with using a traditional PID controller method for low loading situation. So these are the objects we are going to consider in the control strategies method. Physical constraints. What are the physical constraints? Some physical constraints that may be considered in AGC. So that includes the time delay, generation rate constraints, interline power flow controllers, and redox power flow batteries. So these are the constraints of the physical aspects which may be treated in AGC, which may include the time delays, and they may also treated with the generation constraints. So multi-area AGC is scanned for the purposes of increasing stability. This is by means of improved PID controllers under 1% of value. That means about delta P. So two techniques are used to tune the gains of the proportional integral derivative action. So which it is particle spam optimization and fuzzy PID case. So these two methods will much more influence the system parameters and makes the gains turn off to the PID action. So here the main function of the electrical power system in general is to maintain the control to a certain level, and it makes the frequency and voltage to the suitable acceptable limits. So there should be a balance that should be achieved in between the load demand and power generation. This is required to provide the reliability and high quality of the electricity. So wind thermal hydro power plant is mostly based on the atmospheric and cyclic conditions. So due to that, if in case of wind power plant is dependent on wind speed in a particular time period, so some of the mathematical techniques are not applicable in this type of area case. So continuous time linear quadrature regulator, that is called LQR concept, that has been applied in the present systems for the design of the optimal advanced control strategies. So this is relevant to the frequency response enhancement of multi-area interconnected power system network. So if computational processes are involved with intelligent techniques or methods like PSOs, particle swarm optimization methods, and gradient descent techniques, which will be considered to make the systems to be error free. But here in some cases, it is more useful to go through the PSO method because of it is more reliable and more efficient compared to the GD method. So this makes the system parameters as comfort to the given neighboring node. The changes in the power demand affects the frequency and tie-line power flow, which will be in between the control areas. So here the main function of the load frequency control is to maintain the system frequency as it is scheduled value by regulating the active and reactive power cases. So automatic generation control is one type of regulation of the power that will be regulating the output of the governing of the bodies of the generators within a recommended area in the response to the changes in the system frequency, or it may happens with the tie line frequency. So this is going to be achieved when AGC accepts the suitable limits. So here it is used to control the frequency and the preferred tie line power flow as well as to accomplish zero steady state. So here the main aspect behind the modeling of the combined power system and design of the AGC are ready to reduce the wear and tear of the equipment. Then it will slow down the monotonic type of the generation response of the controller, and it must be selected, and it is possible in AGC and frequency error for the steady state that should be expected to zero case. So a control signal is ready to made up of tie line flow deviation. So this should be added to the frequency deviation weighted, and by the bias factor we can accomplish the required object, and it is also known as area control error, ACE, area control error. So there are number of conventional and advanced control methods which we have used as per the requirement, and we may treat it in the simulation atmosphere. So that will going to use the proportional integral controllers. So here there are number of benefits over to use these advanced controllers instead of conventional controllers. That means these PID controllers have some attractive features like reliability, having the quick operation and response, and it will act for more efficient case. So it is has an ability of changing the dynamics of the entire system, and because of this it will be more useful for designing a power system network. So this controller will obtain an error value by comparing a measured process and a designed set point, and it will try to reduce the error as soon as possible. So this may give that information regarding simple implementation of discrete proportional integral derivative controller action. So this gives the suitable results which make the system to be smoother. So here it is required to implement a control system whenever it is operating with applications and the system output is controlled due to changes in reference value. So like several examples of this type of applications are introduced to control the temperatures, motor control actions, force, speed, flow rates, pressure, and any other variables they are going to be introduced in the network. So PID controllers can be used to control any significant up to that time when this variable can be affected by handling some other process variables. This makes the system to be smoothened in all the considerations. So here AGC is used to maintain the acceptable frequencies which may have during the normal operation due to the fluctuations in the load and variable resources case, and as an early possible response to the system, the contingencies like unexpected loss of a generator or transmission loss is going to be follows. So typical sources of AGC may include hydropower, gas combustion turbines, gas combined cycle gas turbines, and gas or coal steam turbines units that providing energy from the portion of their capacity, but that have additional unused capacity of that system that can be ramped up to the 2 to 5 seconds of the time. So battery energy storage system BESS is being widely integrated with wind power systems, this is ready to provide the various auxiliary services. That may including automatic generation control. So that successful operation of the interconnected power system network requires matching of the generation to the load demand and the associated losses. So based on the demand, the operating point of the power system may goes to changes. That may be at any moment of the time, which may result in undesirable effects of the power system network. So here it is undesirable effect that should require a controlling mechanism. So which we will substitute to the acceptable limit, or which may ready to suppress the undesirable effects. So here the load demand in the power system is very stochastic in nature. So which requires an automatic controlling action rather than a manual case. So in general, power system network consists of various control areas. They may represent a group of coherent generators, which is swing in unison, tie lines for providing contractual check changes. That should be in between the power among the different areas of interest. So one of the main problems of the power system network is here to maintain the frequency and power exchange at their rated values. So various power system controllers have to be evaluated over the few decades of the time, so to keep the power system in a secure state and protect it from various black holes. So some of them are generation excitation controls, prime mover controls, generator or load tripping cases, fast fault clearing cases, high speed reclosing voltage control, or reactive power compensations. So load frequency control and current injection methods also used. So in the recent times, other methods like static wire compensators, high voltage direct current converters like HVDC transmission systems, FACS controllers, and wide area power system stabilizers. So they are required to control increasingly be used to solve the power system oscillation problems. So but the load frequency control is still retains its importance because of it forms as an important case. So integral part of the automatic generation control is playing a very key role in the power system network. So here automatic generation control is a centralized integral control which will balances the total generation and load, and it will be added with the losses to reach the nominal system frequency, which is about 50 to 60 Hz, and scheduled of power interchange with neighboring systems are going to be taken place. So for large scale power system networks, when they are going to be interconnected areas, this may result to the summation of all the complex variables. So as they well designed and operated for power controlling system aspects, they are essential to cope up with the load changes. So this may makes the disturbances providing acceptable power quality, and while maintaining both voltage and frequency, they are going to be operated at tolerable limits. Within acceptable limits, they are going to be treated. So load frequency control is being used as part of the automatic generation control. So this scheme is an electrical power systems which maintains the system frequency under the nominal values case about 50 to 60 Hz. And in the power system network, LFC has an auxiliary service which will play an important and fundamental role. This is ready to maintain the power system network in an appropriate level case. So here it is required to maintain the system frequency and tie line power interchanges. They are to be scheduled under various values cases. So here the main aim of the power system controlling objective is ready to meet the measuring of the controller error signals. They are called the area controller errors, and which represents the real power imbalance between the generation and load. So has it to be designed much more importance and important research with the changes of power system structure, type, size, and complexity of interconnected networks are follows. So one of the turbine governor control mechanism is introduced in this AGC. So that governor is a system that actually and instantaneously adjusts the rotation of the speed of the generator. That is going to according to the frequency variation. Contributing to the restoration of the frequency to the nominal frequency of the power system. So governor is equipped with the most hydroelectric and thermal power generation sets in the resulting aspects. So the main effects of the governor, which will include the following points, that is quickly covering the imbalances between the output power and the load demands with the ongoing existence of the frequency deviation. And one more is changing the power flow in the power system network. Effectiveness of the primary frequency regulators depends upon greatly on the damping characteristics. This may also plays a key role. So smaller the slope, that means which will be considered with same load changes leads to smaller rate of the change. Greater the adjustments that may affect. So if the drooping characteristics are horizontal in nature, it is to be known as synchronous governor. That means here which will ensure that the frequency does not change as the load changes until the turbine power limit is going to be exhausted. So this type of governor is only used in the independent power grids with only one generator, and it is going to be responsible for controlling the frequency range. So governor droop characteristics are supposed to be represented here. So these are the governor droop characteristics. What we are going to consider on either axis means here the x-axis will represent output power. So that should be considered here. This is the output power. In megawatts we are going to treat, while y-axis is the electrical frequency. So which will shows that electrical frequency of the power system is considered in hertz. We will start from minimal basis to the up to a 54 Hz. So usually Indian frequency is about 50 Hz. We can extend to some more, and the drooping characteristics are asynchronous in nature, and which may be about 0%, 3%, 6% in drooping in manner, 6%, 3%, and 0%. So asynchronous nature will reaches from 0%, and as the characteristics are drooping in nature, the performance of the curve may droops, and which will be frequency dependent nature according to the respective power ranges. So turbine governor controller here is required to regulate the generating capacity of the generator through various control signals. So this will act on the valves or gates to change the mechanical power output of the turbine. So thereby we can change the generating capacity of the generator. So here main task of the governor system is to maintain the generating capacity of the generator with a suitable predetermined point values. So whatever the representation in the turbine governance mechanism, so that will be representing as a transfer function. So it contains some following functional signals: the measured system frequency, that is Fmeas, and the reference frequency F reference are compared to calculate the frequency deviation. So these deviations are to be known as error signals. Then what happens means if the error signal is outside the deadband, it is to be amplified by block KGI and added with the secondary control case. So that secondary control is represented by DPGI, that is generator G in the area I, which is the AGC output. So KGI is the drooping characteristics of each generator G in the area considered I. This is the generator G. Here area is represented with I. So here it should be noted that when the governor is in the first stage of the primary frequency control loop, so DPGA has not been sent to the governor from the AGC case, which will be treated to 0. So governor will immediately adjust the power of the generator so that frequency does not goes to decreases or increases very much. So when the DPGI signal is in input nature, governor will going to increase its or decreases the power to meet the secondary frequency control. So requested power signal then passes through the turbine governor's characteristics. So this is going to be controlled to the suitable extent by means of the ranges of the signal supplied. So the limit block, which is created to limit the power output of the turbine or valve gate of the fuel opening closing valve, is going to be considered. So this is with a value from 0 to 1. That means output signal PGTI is the generator's capacity that would be treated after the adjustment case. So this is the block diagram presentation. Whatever earlier we considered as the measured value is given to the reference section, and it is going to be excited by means So one of the deadband is provided here. This is connecting to the KGI aspect, and this will be generating one of the signality DP9, and 1 by 1 plus ST9 is going to be considered. These are suitably applied with the limits PTI9, and this deadband will make the system frequency to the response cases. Here we will introduce some algorithm, that is AGC algorithm for a basic two area power system, which will use ACE, area control error concept, as a monitoring signal, and it will set it to 0 in the event of changing the balance of the generation power and the load on the system. So ACE signal includes the deviations of the system frequency, and it will interchange the power between the two areas. So the algorithm aims to ensure that any power imbalance that may occur in a particular area of the power system network, that is promptly corrected in that same area case, that will be intersected with each other under various boundaries. So here adjustment to return to the power balance is performed by AGC secondary control signal in that particular area. So here one of the three equations are represented with the ACE1, delta PG and delta F. ACE1 will goes to delta PT plus beta 1 delta F, and delta P becomes summation P of the power flow frequency minus reference frequency, and this delta F is the measured power minus reference power, which will represent the expression of ACE, means the related elements are coincides with each other under reference and flow rate cases. So this resultant values makes the change in frequency at delta F case. So here AC is the area control error of the particular area I. Delta Pij delta is the tie line power flow error between bus I and J. So beta I is the frequency bias coefficient of the area I, and delta F delta is the frequency error of the power system. So whatever the second expression represented, that will be interchange the power deviation, where power flow is the exchange power on tie line case, and there is a total K tie lines connecting to two areas as a power line flow reference, which will be the reference set of power exchange in the tie line cases. So third expression representing the frequency error of the system, where measured value is the measurement of the frequency at which the rotor and reference frequency is the nominal frequency of the system representation. So these three considerations based on the system criteria are designed to operate at suitable frequency ranges. So here AGC controller is applied to both the areas, and they may determine each of the area control error under area I for each area, including ACE1 and ACE2 cases. Now here it is assumed that there will be decremental in the generating capacity of the power source with the area 1, that may causes the frequency deviation. So generators in area 1 have enough spinning reserves. That means they will take on the task of the returning the frequency to the nominal value, that is ACE1 equals to 0. So power adjustment at the generators is only made in the area 1, so there is no change in the area 2 or generation of the tie line flow. So by that we can adjust the required generator levels under area 1 and area 2 with the consideration of area control error concept. So here if the reserve capacity of the area 1 is not enough made, then area control error 1 still exists because of change in delta, that is to be non-zero case. So at this time the remaining delta P12 and delta F are switched by excess powers from area 2 to compensate for area 1, and they may helping to bring the area control error 1 error to 0. So here frequency is stabilized under the referential case. So the lack of power in area 1 can be completely compensated for by the amount of power from the second area case. So in the essence of this controller case, there may be some restoration of the frequency to a stable value of the reference case. If there is enough reserve power for the secondary control, that must be compensated at various aspects. So these are the aspects which may cover, and in the second part we may treat some more points with the variable controllers case that gives the suitability of the AGC two area power system network. So these are some of the references, and which may give some brief information. regarding AGC concepts in one area, two area, and multi-area cases. So, which will be better useful. And thank you.
Like, share and subscribe. Hit the bell icon for more updates.